Okay, so we have this problem up on the board. I'm going to read it aloud here in case for the afternoon session and for anyone who's missing. So, again, I just didn't feel like spelling out rhinoceros. So that's why you see rhino. Okay? All right. Okay, so it says if a rhino/rhinoceros moves at 10.10 meters per second squared and collides with a car, what is the force on impact with a car or the car? The rhinoceros has a mass of 1610 kilograms, and what is the momentum if the animal initially was moving at 1610 meters per second? Okay, so it's at this time, you have, if you're tuning in later, maybe you want to hit pause so you can work on your own. These are just atoms for the organic class. This is just terms for the biology class. Don't worry about those. I just don't want to erase them. Then I got to try to remember what it was that we had talked about. Okay. So for the 14, I think we're up to maybe 14 times. I just make that number up. Is it 15? Yeah. So for the 15th time, you have read the problem. What would the next step be? So what do we know?
Mass is 1610 kg.
Okay.
Acceleration is 10.10.
Okay. You're correct, but I want you to know why you are correct. The label tells you that. It says it's moving. Well, it's moving down here too. So by the labels, this is a specific variable, just like that is a specific variable. So we can presume that that is the acceleration, which it is. What else do we know?
1610.
Okay. I was just going to ask, can or do we need to be more specific than that? And we're going to answer that here in just a moment. Okay? Is there anything else that we know?
No.
Okay, so what is the question asking?
What is the momentum of the animal?
We see this, and then what is the momentum? Okay, so we need to find the variable p for the momentum. We need to find the force. One of those is actually pretty simple to find. Just tell me.
Force is
We can do the force because we know what does force equal.
mass times acceleration.
So if we multiply these two by doing what the formula tells you to do, which is saying that for any force, it's going to equal your mass times the acceleration. So rather than looking up here at the problem, we have the information that we need right here. And then notice we're not labeling these as we go because we've accounted for that over here. So therefore, 16,261. Point whatever, maybe there isn't a decimal, but we're labeling that how? N for newtons, okay? So that takes care of this one. So we've got our force now. So we need to calculate the momentum. What velocity is tied into any momentum? It's your final velocity. When we look at this, we don't have the final velocity. We only have the initial. And I see I have failed you as a teacher. Just hang on just a moment. I found it because this took place, not took place in 2.45 seconds. Okay? Because
And then
So we know that variable now. So once we put that down here, if you have a really good understanding, can someone tell me why we might have needed that time?
Variable.
Because in the acceleration formula, what are your variables?
Final velocity.
VF, VI, and time. So if we need to find this momentum, which we do, we know that a momentum is the mass times the final velocity. But we don't have that final velocity. We only have the initial type. But would you like to work on that yourself?
No.
You want to do it, work on this together?
Yes.
Okay. So how can we find that final velocity then? Do we have an acceleration?
Yeah,
Yes.
Where does that belong in our equation?
on the right, the left.
We're going to put it on the left. You could put it on the right, but it just makes more sense to put it over here. Then what do we have on the right-hand side of that equation?
Initial velocity and then VO and then IV.
Well, we don't need to put VI in there.
16.20.
Okay, so 16.10. And then what?
Divided by 2.45.
2.45. Okay, so we've got this fraction here. And if you wanted to, yes, you can put this into parentheses. Maybe that's good practice. I mean, there's nothing wrong with that. And sometimes it's better to be consistent with this, because one of the things that I like to maybe point out is, let's say it's during the beginning of a basketball game. Maybe it's still in the first quarter. It's still maybe midway through the second quarter. Okay? There's a made shot. Coach calls timeout. Okay? So during the course of a game, what can a player do after a made basket on the baseline?
Celebrate.
Okay, so you have to take the ball out of bounds. What can you do with that ball on the baseline as you're inbounding the ball? Exactly. You're going like this, saying back and forth. So when you look at an official, there's no one guarding them in front of them. It's just the person taking the ball out of bounds and then the point guard, whoever. It doesn't take a rocket scientist to say that the official's still going to go like this. Okay? But that player is not going to go running up and down the baseline because there's no one guarding them. Does everyone follow what I mean?
Yeah.
Okay? The reason that that's so important is now maybe it's in the second half and there's less than a minute left and it's a close game. Well, if that basketball official is used to saying, we've got this, and they keep practicing that, it's just a good habit to do that, whether it's in the first half or the second half. Okay? So in this case, it's just good habits to do things like this. How do we get rid of our fraction? We can cross multiply. And I'm just anticipating what you're saying because we've done it so many times. What can we do to this number here? Put it over 1. And that's what we've been doing for a long time. Okay? So what is 1 times VF?
VF.
Okay? So that gives us VF. What else would we get? See, now we're going to make you think a little bit.
1 times 16.10.
And that gives you what?
16.10.
And don't forget our negative sign. So we've taken care of this. We've got our equal sign. Now what do we need to do?
10.16 times 2.45.
Okay? And in that case, what do we get? 0.745, which would be 0.75 then, rounding up to 2 decimal places. Okay? So we need to get this variable all by itself.
Minus 16.10.
Well, that's going to give us a positive value over here.
Add 16.10.
Okay, we're going to do that to what though?
16.10.
And the other
And the other side. So if we're going to add 16.10, we have to do that over here. Okay, those are now gone. So our final velocity then is,
40.85.
that still shows up on the camera, 40.85 you say?
Yeah.
Okay, that's meters per second. Now we're on the home stretch. Because now if you have your final velocity, what can you do now?
Solve it for momentum.
Right. So what does our formula tell us to do in our momentum formula?
Mass times final velocity.
Okay. So we can get rid of all of this. We don't need that anymore. We don't need that anymore. We don't need this, and we don't need this, and we don't need that. Okay? But we still need this mass because according to this formula, okay, what's the variable for momentum? So what does the formula tell you to do on the right side? Okay, so here's our 1610. And then our final velocity we calculated was
40.85.
40.85. You multiply those two. And we get 65678. 6768.
Yeah, 65768.
Okay, and then point whichever. And then how do we label this? It's a kilogram. What? It's per meter. We're not subtracting, per meter per second. Okay, so there's our second part of what this was asking for. 656,768, and then whatever it was, I had erased that 16,000 something it looks like. Okay, so one of the things that, again, what we see happening is you have to look at the variables that you have, be able to, some of them are really easy to solve because you already have the information. But then we want you to think critically, okay, let's look at the information that we have and then see what we can solve for to maybe unlock one part of a problem and then do that for another. Because, are you excited for, what would you say, today's homecoming game or tomorrow's?
Tomorrow.
The Amazing Race?
Yeah.
Mwah, ha, ha, ha. You know why that is?
Why?
Because part of that amazing race is trying to navigate your way through this room.
Are you gonna make us solve like the?
Yeah. Not anything like that.
Can it be like 2 + 2?
You know, it might not be that difficult.
Okay.
Okay, I mean, I said that wrong.
Yeah, but
It might be that easy, but you have to use Bob to do that addition.
okay.
So the clues will give you the numbers. It might be simple addition, but it's trying to navigate your way through those clues to use Bob to help you.
So there'll be like numbers on it, and you have to get those numbers and then get
Mr.
them.
McKenny.
Then add them together.
Mr.
Yes.
McKenny, are you gonna have us spell a word and then figure out the numbers that go with it?
Something close to that.
No. I
Yeah.
hope we don't get his.
So do you determine who shows up for the? Okay, we don't need to be. We'll come back to that in just a moment.
Each turn.
Okay, so next week we're going to assign another problem-solving worksheet. This, you know, if you copy this down, this will probably help you because that might be something very similar to on there. And then your vocabulary evaluation on Tuesday. The arch, okay? Something that you get to do, okay? I always just keep this as a template. This is what I call the keystone. When you look at any arch, what you will do is you are the engineers. You will take tongue depressors, and if you were doing any type of finished woodworking, does anyone know how you can bend this? I mean, yeah, see, you can bend it, but it goes
You have
back
to
to its
rub it.
original shape.
Rub it. You have to rub it.
Okay, that might not be too far off. I don't know if soaking it in water is pretty efficient.
Warm water.
Exactly, because we have a sterilizer next door. How many of you like, let's say, any type of chicken, whether it's from Pizza Ranch, Kentucky Fried Chicken, wherever? It's probably not baked in an oven. It's probably pretty similar to a sterilizer. A sterilizer is just a pressure cooker that is pushing that steam. That steam, of course, is really hot. Pushing that steam into here. Then when you pull this out, this is really, really flexible. And then once you bend that, it will keep its original shape, because now we got a bend in there. But we let go, and it pretty much goes back to normal. But what you do is you design how you want this to bend to make an arch. If this is 1/2, then you do this in a set of maybe 8 sticks, maybe 10, because they have to occur in pairs. Because if you have one on this side, you would have to have one on this side. And what you do is you lock this into this keystone, and then we try to, not try, we'll determine how much weight these can hold. We won't quite get to all of that next week, because we need to see, it's a video called Modern Marvels about the arch, and it shows you what an arch actually looks like, because there's different types of arches. There's also, you could say, close cousins like the vault, the dome, and cylinder. Those are all different types of arches that have the same type of characteristic. Then when it says arch design, after you pull these out of the sterilizer, you design the type of bend that you want in here. Some people do it quite drastically. Other people maybe don't put enough bend in there. But that's where you learn about this, because some people in here might be interested in engineering in the future. So it's where you take this content that we've been exploring and calculate the forces that these things can hold. That is next week. Okay, so the rest of the time you can work on these papers. Some of you don't have your vocabulary done. It's a great time to get that done. And I will be collecting those papers here in just a moment. So that's next week. And what we're doing today, we'll catch up to you next time.